While gas turbines have traditionally been used as jet engines, when it comes to other applications like running cars or generators, they have been impractical and expensive. Even when in theory, gas turbines offer more efficiency and are fuel independent.
There are now materials that is much more cheaper than the methods, manufacturing methods, which are so cost effective, and the advancement like 3D printing can make small gas turbines possible today in this world. Our system is derived from the aircraft engine and is going to be extremely reliable, and the maintenance or the service cost will be close to zero, and this will augment extremely cheap power for the end user.
The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists, and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
Hello and good day to everyone. Thank you for joining us today. On behalf of the Office of Global Engagement, it is my pleasure to welcome you to the 58th webinar from the IRIS webinar series. My name is Richu George and I'm a part of the Office of Global Engagement at IIT Madras. The Institute of Eminence scheme was launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research facilities. IIT Madras is proud to have been selected as one such Institute of Eminence. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway at IIT Madras. As a part of these initiatives, the IRIS webinar series aims to showcase the innovative research being generated to various stakeholders like the students, researchers, industrialists, and policymakers. From the Advanced Manufacturing Technology Cluster, the research initiative presenting today is titled Applied Magnesium Research, led by Dr. Sushanta Kumar Panigrahi. The focus of Applied Magnesium Research Group is to establish magnesium-based science and technologies towards various forms of magnesium manufacturing and transform magnesium technologies from laboratory scale to application level with respect to futuristic mobility. To introduce Dr. Sushanta, who is the principal investigator of this research initiative, Dr. Sushanta is an associate professor at the Department of Mechanical Engineering at IIT Madras. His fields of research are magnesium manufacturing, microwave technology in manufacturing, high-performance engineered sheet manufacturing, advanced metal forming, innovative material processing, and material development for improving manufacturability and structural efficiency and solid-state joining. He has published 83 research papers in international journals, 38 in international conferences, 6 book chapters, and filed 4 patents. His Scopus H index is 30 and average impact factor per publication is 4.9. Thank you for being with us today, Professor Sushanta. Now it is my pleasure to introduce the moderator for the webinar today, Professor Surendra K. Maria. Professor Maria is from École Centrale de Nantes, France. He was a full professor at ECN Director, Graduate School of Applied Mechanics during 2003 to 2007, and Deputy Director at International Relations during 2003 to 2005. Professor Maria has more than 150 research publications, 3 industrial patents, more than 30 keynote invited presentations in reputed conferences and meetings, and above 20 invited lectures in academic institutions across the globe to his credit. He is one of the most recognized global researchers in the field of advanced manufacturing and materials. Thank you for joining us today, Professor Mario. We're very excited that you could be a part of this session. We also have a very distinguished panel with faculty from universities across the world and various departments at IIT Madras joining us at this session. With this are Professor Guillaume Raxina, Professor Kiran Solanki, Professor Manoj Gupta, Professor John Banhart, Dr. Francisco Garcia Moreno, Dr. Anand Krishna Kanjala, Dr. Ilaksh Adalaka, Dr. K. Hariharan, Dr. Lakshman Neelakandan, and Dr. Manas Mukherjee. A very warm welcome to all of you. And before we start, a note to the participants, please use the Q&A to enter your questions and upload questions that interest you so that the moderator can prioritize them later. Over to you, Professor Sushanta.
Thank you, Richi Madam. Good evening, good morning, and good afternoon to all the participants across the globe. So welcome to this IIT Madras Research Initiative outreach talk on applied magnesium research. So before starting my presentation, I would like to thank the Ministry of Human Resources and Development for funding this research initiative through Institute of Eminence of Center of Excellence scheme of IIT Madras. I'd like to thank the Director of IIT Madras for taking the initiative of this and sending our proposal to different forum, different reviewers, and I would like to thank all the reviewers for approving our proposal for to establish the center. So thank you very much. So in my presentation, I have divided my presentation into 4 parts. In the first part, I am going to tell about the key focus of our applied magnesium research group, and I will introduce about the group members. Then in the second part, I will speak about the potential of magnesium alloys and composites in mobility sector and their current applications. In the third part, I will tell some research glimpse of Applied Magnesium Research Center, which is already available in this particular website. And if I will get time, I will focus the third part. Otherwise, I will skip the third part. Then the fourth part is about key focus, vision, and proposed activities of Applied Magnesium Research Group towards science and technology development. So as for this flyer, so our key objective is for technology development. First, we will understand the fundamental application-based fundamental. We will do fundamental-based application-based fundamental research, computation-based fundamental research, and manufacturing-based fundamental research to establish different form of manufacturing technology for a different form of magnesium manufacturing. So we have several several team members. I will introduce all the team members and several international collaborators. And we are in the process of collaborating with industries for our center. So we have 6 team members in our group. Dr. Anand Kanjala from and Dr. Anand Kanjala is from Metallurgical and Materials Engineering Department. Dr. Ilaksh is from Applied Mechanics. Both are having expertise on computation-based fundamental understanding of magnesium-based research. They will help us in this direction. Dr. Hariharan, he is from Mechanical Engineering Department. He is expert in forming magnesium. He is showing so low formability. So his expertise will help us in improving the formability of magnesium-based research. Dr. Lakwan is expert in. Dr. Lakwan is from Metallurgical and Materials Engineering. He is expert in corrosion science. His expertise will help us in establishing the improving the corrosion potential of magnesium-based research. And Dr. Manas Mukherjee is from Metallurgical and Materials Engineering. He is expert in technology development of different form of metallic foam. So his expertise will be helpful on establishing different technologies for developing different kind of magnesium-based metallic foam. And I am working on different kind of technology development for seat development, clad development, and mainly I'm focusing on metal development, metal processing, and microstructural engineering based. Okay. We have 6 foreign collaborators, Professor Marino, Professor John, both are from Humboldt Center of Berlin, Germany. Professor Manoj Gupta is from National University of Singapore. He is with us today. Professor Surendra Maria and Professor Guillaume Racinac was both of them are from Ecolo Central and France. And Professor Kiran Solanki is from Arizona State University, USA. They are our international collaborators. So our magnesium is a potential material for mobility sector. So first, let us know like what are the requirement for what are the material requirement, desirable material requirement for mobility sector. When mobility sector in the form of road mobility, air mobility, and water mobility. The material to be used in mobility sector should be should provide fuel efficiency. It should be plentifully available in nature, and it should not cause any harm to the atmosphere, and it should be cost effective, so that it should have low cost, and it should have good structural efficiency, means its strength should be higher, lightweight, and all it should have all functional requirements, and it should have manufacturability. So all these properties are required for a material to be used for futuristic mobility to be used for mobility applications. Okay, so this slide shows few pictures. Nowadays, CO2 emission is the biggest challenge. We have a lot of vehicles, and because of so many industries, they pollute the atmosphere, and because of so therefore CO2 emission forms. So because of CO2 emission, you can see that in December 2017, a cricket match between India and Sri Lanka was held because of significant pollution, atmospheric pollution, and in June 2018, it is a peak summer, but still you can see that we cannot visible. It is not visible outside. Is not visible because of significant pollution due to CO2 emission. This is in April 2019 in Delhi. You can see all are using masks. Delhi became fully polluted because of significant CO2 emission. So CO2 emission is the biggest challenge. It causes significant impact on environment. It also impacts on global warming. Because of CO2 emission, the global temperature increases, rise in global temperature happens. Because of that, sudden climate change happens, and due to sudden climate change, we get irregular activities like flood. In 2015, we found a flood in Chennai. In Odisha, we found many cyclones, and in France, the forest fire often occurs because of this, and in many other countries because of global warming. In global warming, because of significant CO2 emission, the global temperature increases, and because of the climate changes, and we get this kind of irregular phenomena. And this slide shows like how the global temperature increases year by year. You can see in 1980 there was very less global increase in global temperature, and now in 2019 it has increased to around 1 degree rise. So there are so many agencies which takes care of this part, like to understand, which controls the climate change. And that committee in Paris Agreement, they told that if the CO2 emission will reach, the CO2 emission should be much lesser than 2. If it will reach 2, then that is a challenge, and some irregular phenomena will happen, and in that case, in that situation, significant effect of irregular phenomena like floods, droughts, cyclones, etc. will happen. That is undesirable. Therefore, the society, climate change society, like in Paris Agreement, they made a target like CO2 emission by 2025. The CO2 emission should be cut down by 2 billion tons. So all the resources through which CO2 emission happens, they have got a strict guidelines that they have to do something so that CO2 emission will be reduced. So then like this slide shows how the what are the sources of CO2 emission. CO2 emission happens because of industry, biogas, dust, others, and vehicle. And among all, the share of CO2 emission comes from mainly vehicle. 35% of share of CO2 emission comes from vehicle. And there are the different kind of vehicles like domestic flights, medium car, and this slide shows this part, right part shows how each vehicle is contributing the significant impact of CO2 emission. You can see when a spacecraft or aircraft goes, it pollutes the atmosphere significantly by emitting a lot of CO2 emission. When a car goes, significant CO2 emission happens. Therefore, a lot of strict guidelines, and it should be cut down as per the guidelines. So, a lot of restrictions are there for automotive manufacturers, so that they have to manufacture the automobile and transportation sector, so that the CO2 emission will be less. So you can see that in every vehicle in India, you will get a sticker like this. It tells that if you want to ride a vehicle, we have to pass the CO2 emission standard of our vehicle. So then what are the remedies? The remedies of CO2 emission in mobility sector, the greatest remedy is weight reduction. If you reduce the weight, then the fuel consumption will be lesser, so the CO2 emission will be lesser. So among all the factors, weight reduction is a significant factor for reducing the CO2 emission. So then the material comes to picture. So the lighter material will have more weight reduction, and it will reduce more impact on CO2, and it will reduce more way of CO2 emission. Among all the materials, magnesium is the lightest weight metallic material. You can see from here, magnesium density is around 1.78, and which is 1/4 lighter than steel, and that 40%, 35% lighter than that of aluminum. And magnesium is the lightest weight metallic material, and hence it is a potential material for significant reduction of CO2 emission. Now, if you use magnesium, what will be the impact of magnesium on fuel efficiency and cost effectiveness? So magnesium weight reduction has also a significant impact on fuel efficiency and as a resultant effect of cost effectiveness, because as the weight of the vehicle reduces, then the energy required for fuel consumption will also reduce, and as a result we will have greater fuel efficiency. So there is a direct weight reduction has a significant on fuel efficiency. For example, in a passenger car, if for every 10% of weight reduction will result in 6 to 8% of fuel saving benefit. So, for example, currently the passenger cars are made up of mainly by steel and few aluminum. If you totally change that to magnesium, we will able to significantly reduce the fuel, around 36 to 48% of fuel improvement we will get, and that in turn will reduce the CO2 emission. And so we will get significant impact. And therefore, since magnesium is the lightest weight structural metallic material, hence it is a significant candidate for influence of fuel efficiency and cost effectiveness. This is a second example, like if you in the air sector, mobility sector in air. So spacecraft, the spacecraft for the cost of spacecraft into the GTO are estimated to be approximately 20 lakhs per kilogram. The cost for launching a satellite in LEO by space shuttle is about 40 lakhs per kg. So weight has a significant impact on this one. So if you reduce the weight, you can per kg weight reduction will lead to 20 lakhs benefit, and a spacecraft contains lot of weight. So this is a significant impact. A weight reduction causes significant impact on cost effectiveness in space sector, and by reducing the cost also, by reducing the weight also, it will increase the payload capacity with reduced cost in any spacecraft. Therefore, magnesium plays a significant role. Magnesium, since magnesium lightest material, it will provide significant. It will act as a significant candidate material for improvement of fuel efficiency and cost efficiency in case of space structure. Now, next is magnesium plentifully available. If you see the this one, and the generally in the crust of Earth, all the minerals are available, and this crust lies in the range of around 40 kilometers in the top layer below sea level throughout in our planet. If you see that one, these are the 10 most available abundant elements in the Earth's crust. Among 10, magnesium is the fourth. So oxygen is a gas. So silicon is the first metallic material, aluminum is second metallic material, and iron is the third metallic material, and magnesium is the fourth metallic material. It contains 2% mass of the total Earth. So this much of magnesium is plentifully available in earth crust. So this is not available in direct form. This is available in the form of a mineral or ore, dolomite or brucite or magnesite or anything, and then it has to be extracted from the ore to get a real life component. Therefore, magnesium is a God-gifted element. Magnesium is also available in seawater. You can see that magnesium is third most dissolved mineral in seawater, and magnesium is the first most dissolved mineral in metallic form in seawater. It means magnesium is plentifully available in seawater as well. So magnesium is again a God-gifted element. And then next question is, how much amount of magnesium is available in India? So magnesium, according to this report made by the assistant director of NML Jamshedpur, they made a report, and according to this report, there are plenty of dolomites are available in sea of India, in Odisha, Bengal, Bihar, Maharashtra, Madhya Pradesh, Madras, Mysore, Punjab, Rajasthan, many places. And the key selling point is, in a single place, when they did analysis, they found that 252 million tons of magnesium minerals are available at a span of 60 miles in only one part of India. So this is the significance of this magnesium available in India in sea structure. Now, when we use magnesium, it has to, after using magnesium, we have to throw magnesium after end use. So now the next thing, is it causing any harm to earth? So the research says that when we throw magnesium to earth, it will go to earth, and that will our plant needs magnesium. So you can see that there are two pictures of this leaf. The first picture shows that in this leaf color is yellow. This is due to low magnesium deficiency. However, with adequate magnesium, the leaf color becomes green. According to this literature also, they varied the magnesium concentration in the soil, and they found that with adequate magnesium, the leaf is green, and with the poor magnesium, the leaf is yellow. So the magnesium plays a significant role in plant growth and leaf growth as well. So it is a very good material for earth also. Now, if you see what is the friendliness between magnesium and aluminum waste, this literature says that magnesium is first part, says that magnesium is a desirable material for plant growth and plant leaf growth. And the second literature says that aluminum is a toxic material and which limits the plant growth and development of many acid soils. So aluminum is a toxic material. We cannot throw aluminum in the earth. It causes the harm to the plant. However, magnesium is giving positive impact to the earth. This is a good impact. So magnesium is also used for our body applications. Our body needs magnesium. After iron, we have magnesium in our body, and if magnesium gives good energy creation, protein formation, muscle movement, and many other advantages. And if we have magnesium deficiency, doctor prescribes to take the magnesium tablets, and this is a kind of thing. So magnesium is also beneficial for bioimplant application. Magnesium property similar to our natural bone, density similar, and all other properties are more better than the bone. And people tell that magnesium cannot be used for real life application because it is flammable. Actually, it is not so. As per the International Magnesium Organization, they told that magnesium is safe up to the melting point. It will not cause fire up to melting point. So when we use magnesium for different applications, for example, in spacecraft, when it goes at high speed, there also the surface doesn't get a temperature more than 150 degrees centigrade. So nothing is going to happen because it's according to this paper, magnesium will not cause fire up to the melting point of magnesium, and the melting point of magnesium is around 660 degrees centigrade. Now, what is the potential of magnesium? So therefore, we realize that magnesium is a very potential material because it satisfies all the bullet points. And in addition to that, magnesium is also a very good potential material. It is having excellent strength to weight ratio, very good machining properties. It means it is having good manufacturability. It is having good damping characteristics. So it means if some accident or something will happen, it will observe the damping characteristics in a very easy way. So this is a positive sign to be used for a mobility material in mobility sector, and it is also giving good biocompatibility. So magnesium is an excellent material for mobility sector. Now I will show you some of the slides of application of magnesium. Magnesiums are extensively used in different applications. These are some applications in cast magnesium alloys. Wherever the lightweighting is required, magnesium is being used. Magnesium is used in mobile phone, laptops. This laptop is fully made up of magnesium, 13.3 inch. Whole weight is around 13.3 kg, and we got the source from Professor Manoj Gupta, who is also available in this panel today. Magnesium is also cast magnesium are extensively used for aircraft, different components of aircraft missile components, aircraft engine mounts, etc. The cast magnesium are also used extensively for automotive applications, like gearbox assemblies and different components of automobile applications. You can see here everywhere magnesiums are used. But in wrought, so now I will show you some of the applications of magnesium in wrought sector. The first magnesium application appeared in the B-36 peacemaker aircraft in 1946, and they used 88,620 kg of magnesium in different form: seed form, rod form, post form, every form. Then in this particular vehicle, 1951, they used so many magnesiums. Then onwards, in many components, they used magnesium. Then in automotive sector, first magnesium application came in 1955 in the international metro light delivery truck. So they used many components of magnesium. The Mercedes-Benz introduced magnesium in 1955 in the racing car, where lightweight is prime requirement. In Chevrolet, they use magnesium, and there are different components which are being used for magnesium. This is most recent. Whole bus was made up of magnesium, wrought magnesium. By using complete magnesium, they could able to reduce 780 kg. The vehicle become light, 780 kg lighter than the earlier one, which is a significant contribution because of magnesium. Everywhere magnesium is used, and magnesium is a future material for electrical vehicle. Because of its lightweight, it will reduce the CO2 emission, and that is the benefit. And it will, because of its significant lightweight, it will improve the fuel efficiency, and which will lead to good mileage, good faster speed, and green environment. And recently, few researchers are also using magnesium using as a battery cell. They got success in developing fuel cell for this kind of vehicle, and now they are doing research to develop magnesium in cars. The researchers are from Energy Genesis Cycles, and the magnesium this is the rod alloy requirement for any kind of automobiles. The existing rod components, instrument panel and everywhere. But at present, steel is the leading player. Everywhere they use steel. 70 to 90% steels are used. 10 to 20% of magnesiums are used, but only 0 to 5% of 10 to 15%, 20% aluminums are used. Only 5% of magnesiums are used, in spite of having significant potential. If we replace magnesium for the whole car, a commercial car, we could able to reduce the weight from 50 to 60%. That will lead to reduced fuel efficiency around 30 to 50% lighter. In the space sector, so the payload capacity and cost of the space vehicle system depends upon weight, and being the lightest weight, because every 1 kg weight saving will cause 20 lakhs of saving. So therefore, in the spacecrafts, they have made in these 4 new spacecrafts, they used aluminum as a core material for that application. If we use magnesium in place of aluminum, we will further reduce the weight for 35% lighter. So why magnesium is not being extensively used in mobility sector in spite of having excellent property? It is because magnesium has the crystal structure of magnesium with HCP. So because of this HCP crystal structure, whenever you want to do plastic, develop rod component or in the form of sheet or extruded product or anything, so the deformation phenomena becomes complex. because twins will form, texture will form, variety of slip system. It has basal slip system, non-basal slip system, pyramidal slip systems, and it is a complex microstructure slip deformation to understand. Therefore, it is very difficult for the manufacturers to understand the complex deformation phenomena and solidification behavior, which lead to manufacturing challenges. And it has shown some poor structural efficiency with respect to poor tension to compression yield asymmetry, moderate ductility, moderate permeability, moderate strength property, low stiffness, and poor corrosion resistance. Therefore, a lot of research work is going on to improve all the properties together, but the research work is still in R&D lab, and therefore there is a need to translate R&D level of research to application level. So you can see, because of this the potential of magnesium, a lot of research work is going on in magnesium. Magnesium is a single element. There are so many metallic material, aluminum, magnesium, copper, nickel, copper. Among all, you can see the research potential of magnesium. Each year, the growth rate is 12% per year. You can see in 2018, 2,768 papers were published in magnesium-based research. This is the potential of magnesium in research domain. And in a single year, we found 6 papers published in Nature and Science kind of journals. There are so many advanced journals, but in a single year, 6 papers were published in Nature and Science kind of journal. This shows the potential of magnesium in research domain. Okay, so the key objective of advanced material research group is to improve the structural efficiency, because we saw that magnesium shows poor structural efficiency. Our goal is to improve the structural efficiency, mechanical based, forming based, corrosion resistant based of magnesium alloys, to develop high performance magnesium alloys composites, both in situ, ex situ type, foams, and establish their manufacturability, to develop manufacturing strategies for magnesium based high performance seed development, magnesium based multimetallic seed development, magnesium wrought alloy development, and magnesium forming technology development. And next objective is to improve the magnesium manufacturing potential of existing magnesium alloys, etc. These are, and to develop these technologies, we need fundamental understanding. In order to establish the technologies, the researchers in our center do fundamental understanding like first principle based analysis, crystal plasticity based analysis, numerical modeling based approaches. We do alloy design based approaches, and microstructural engineering based principles we study to establish these technologies. I will quickly tell you some of the glimpse of our research, because time is less, so I will not spend more time. So magnesium shows poor tension to compression yield asymmetry. We addressed that by engineering by imparting different kind of microstructural constituents during manufacturing. For example, here we need tension to compression yield asymmetry is 1. However, all the published papers have shown that there is a significant yield asymmetry in this case. In different different approaches, initially we did nano precipitation. By using nano precipitation, we overcome the tension to compression yield asymmetry problem. By using grain refinement, it became 1. When the grain size became less than 2, there is no tension to compression yield asymmetry. When we integrated in situ reinforcement in A3, there is also, we did not find any tension to compression yield asymmetry. It means by engineering the microstructure through a manufacturing process, we can control the tension to compression yield asymmetry, and that can be directly used for industry application. So similarly, for corrosion, magnesium shows poor corrosion resistance. So by using different kind of microstructural alteration, by alloy design, or by precipitation, or by engineering fine grains, or by engineering ultra fine grain, we could able to reduce the corrosion resistance significantly. And by doing the computational approach also, we study the corrosion phenomena of magnesium alloys. And now we also do the manufacturability, establish manufacturability of magnesium, develop magnesium alloys by processing map development. Processing map tells the manufacturability of any material. It shows the safe zone and unsafe zone of any processing capability. One group developed different processing capabilities of this particular newly developed magnesium alloy, this alloy. And we also do computational based framework to understand the magnesium based plasticity. One group did different kind of solute segregation into magnesium, and they improved the formability aspect of magnesium, microformability of magnesium. And so they understood established the concept via computational based approach as well as experimental based approach. Again, our group members are also working to understand the deformation phenomena of magnesium, for example, twin phenomena, slip phenomena, etc. So we also do improve the superplastic formability. So in this case, magnesium is having poor ductility. Here we try to improve the superplastic formability of magnesium. So we engineered again microstructure, and we found that magnesium is brittle, but we got 16-30% elongation by engineering the microstructure at a particular temperature. So so our material so we developed also magnesium is a poor ductile material, brittle material. So to make magnesium sheet, they do several passes of rolling because it is low duct. So multiple passes of rolling they do. So we established a processing route to develop superductile material in a single pass. We can see that this is base material, and by our process we got the ductility improvement of 2 times without degradation of strength, and it is also showing planar isotropy. So we also established manufacturing process for different forging process of magnesium by engineering different kind of microstructure. The forgeability of we established the forgeability improvement of magnesium, and here we try to improve the structural efficiency of magnesium alloys via in situ composite manufacturing. So here our objective was to nullify tension to composite asymmetry, improve strength, improve ductility, improve manufacturing, improve wear resistance. We selected a parent material. We engineered the microstructure, in situ reinforcement. We engineer the grain size also, and then we manufacture the material. We then engineer the microstructure. This is the best material, this is engineered microstructure. By doing that, we could able to improve the strength to 2-3 times higher. 80 was the parent material strength, and we could able to get 240 megapascal, 3 times strength improvement, and with negligible tension to compression yield asymmetry, and with 4 times increment in ductility and significant edge hardening ability. So then recently we developed a super strong magnesium alloy with high strength, superplasticity, and negligible tension to compression yield asymmetry. You can see our developed material showed a strength of 500 megapascal, which is highest among all the published papers in market, and our material gave a ductility, superplasticity of around 1300% elongation, which is again highest at 5 into 10 to the minus 2 per second. So this is the theme of our goal of our group, and our group is having potential of doing fundamental to translate the research from fundamental to application. That is our theme, and we intend to develop different kind of alloys and composite design for product development. So our frame is a full domain of magnesium. We want to design, our group has potential to design and develop new alloys and composites, and then as per the industrial need, this is application specific, then we can engineer any kind of desirable microstructure, like application specific microstructure. We want to get good strength, we can engineer the microstructure. We want to get good ductility, we can engineer the microstructure. We want to get good fatigue life, we can engineer the microstructure. And then our end product goal is like to develop manufacturing strategies for making foam, sheet, clad materials, in situ composites, and ex situ composites. To develop this technology potential, we want to use some fundamental tools to understand the science, like innovative manufacturing processes in liquid state, solid state, and powder based thing. We want to do fundamental studies on corrosion behavior, deformation behavior, forming behavior, joining behavior, machining behavior of magnesium alloys. We want to study the fundamentals through the numerical based modeling and simulations, like crystal plasticity, first principle based approaches, etc. So we have the full key focus of our group is to develop new alloys based on first principle, crystal plasticity, Calford based, then develop new material, foam development, cast and rod development, ex situ, in situ composite development, then engineer the microstructure by thermomechanical processing, severe plastic deformation, crystal plasticity. Then these new materials will be subjected to different application domain. We study the surface engineering aspect. We have experts in surface engineering. We study the manufacturability of such developed materials. We study the deformation behavior like quasi-static, cyclic, high-speed deformation behavior. Basically, we are going to establish the correlation between processing, microstructure, property, manufacturing correlation in this group. And at present, there are, to my knowledge, our knowledge, there are 8 existing centers, center of excellence of magnesium-based research across the globe, and ours will be the 9th one. And we are, our center is the first center in India, which will take care of the applied magnesium research center. And these are the center. One is in Germany, one is in Japan, New Zealand, Korea, Australia, China, and in India, our center will be first center to develop magnesium. The vision of our center is to become a world-class research hub at IIT Madras with international visibility and leadership in the research domain of magnesium-based science and technology development. So we intend to do that by doing cutting-edge research technologies to developing cutting-edge research to cutting-edge technologies in the all form of magnesium manufacturing and commercializing the technologies by focusing the cutting-edge application-specific fundamental research and publishing the work in high-impact scientific-based journals in the world. High-impact journals of the world. We want to actively collaborate with topmost international and national researchers in the field. So we want to enhance the visibility of IIT Madras in the global R&D arena through active participation and organizing events, hosting of monthly webinars, thematic workshops, leading international conferences. We want to facilitate the students, research scholars, postdocs, and faculty exchange programs between IIT Madras and foreign universities. So this and in the first phase, we are going to do 9 projects. These are the 9 projects which we are going to do in the first phase. Like in the project 1, we are going to establish technology for magnesium-based in situ and ex situ composite manufacturing. Second project is technology development for magnesium-based metallic foam, closed foam manufacturing. Third project is technology development for manufacturing high-performance magnesium-based alloy sheets. Fourth is to develop the technology for high-performance multi-metallic and magnesium-based dissimilar sheet manufacturing. And fifth project is the technology development of magnesium-based micro-manufacturing, micro-component manufacturing. These 5 are the technology-based projects. We have 4 scientific projects also. The crystal plasticity-based computation fundamental research to establish the deformation-based micromechanics of magnesium is the 6th project. 7th project is the first principle calculation-based computational fundamentals to understand the effect of alloy design on plasticity behavior of magnesium alloys. And 8th one is on surface engineering of magnesium alloys and the corrosion studies. And 9th, because magnesium shows poor corrosion resistance, this project will deal with like how to improve the corrosion resistance of magnesium alloys. Magnesium shows poor formability, so one group will study the forming based technologies to improve the formability of magnesium alloys. These are the contact numbers of principal investigators of each project. Each project is will be carried out by a multiple number of faculty members inside our group. I have only mentioned the key principal investigator name, but however, in each project, multiple faculty members are also working together to develop these things. So this is the opportunity of our group. So we want industry collaboration to establish the technology. We want in university collaboration from international level and national level. We want collaboration with national labs. And we want the joint PhD programs at international level and national level. We want a joint PhD program. We want student faculty exchange programs. So all these things, all the opportunities are there in our center. This is the website of our center, www.thisappliedmagnesiumresearch.org. So we generally update our research activities in this website, and we update the upcoming events in this website. Our next upcoming event will be like inauguration of our center on 21st October 2021, and we are going to initiate an international webinar series and magnesium talk series after this inauguration. We want to conduct so many workshops, international workshops and international conferences on magnesium-based research and applied magnesium-based research activities. So before closing, I want to acknowledge On behalf of Applied Magnesium Research Group, I want to acknowledge the MHRD, Ministry of Human Resource and Development, for funding this scheme through Institute of Eminence IOE scheme. I want to acknowledge the director of IIT Madras and the team members of IIT Madras for sending our for approval for taking necessary action for sending our proposal for different reviewers, getting the reviewer remark, and giving us all the freedom to do research, our research-based activities in our center. We want to thank all the reviewers who approved our center after a peer review process. We want to thank all the collaborators of our center, past and present collaborators, and many of the research. We want to thank our past research scholars. I have not mentioned any name of the research scholar because we have been working in this center, in this magnesium research since last 10 to 12 years. So many research collaborators are there, so many research scholars are there. We want to thank all of them. We want to thank the global office team for arranging this for this logistic based arrangement for this research for this presentation. Thank you very much. Now I'm open for the technical discussion.
Professor Maria, we can go through the Q&A and discuss the questions from the audience.
See, on my computer, I really don't see any question at all for the moment.
So there is a Q&A box. So there is a chat box and a Q&A box. The questions will be coming in the Q&A box.
Okay, this is what I'm looking at.
No.
Oh, okay, I can see here.
Yeah.
Okay, I'm just going through because it seems to me there are so many questions. Yeah. So if I read some 5 or 10 questions, the question that comes to mind is that why people are still using so much steel and aluminum, and how is that magnesium is still not used? Because but Professor Sushanta told it's a very nice material, it's a God-given gift. So the people are asking why steel, aluminum, and steel are most used materials in different mobility industry.
Yeah, so I will address, but I want Professor Manoj Gupta to address this because he is also expert. So then I will also speak.
All right, I can answer this question like that, with the time, technology changes. And when the technology changes, we have to change the materials also. If you go back in before 1980s, the fuel consumption was not an issue. We had a lot of fuel and everything. People did not know about the climate change as much as we know it now. Then what happened is that in 70s, they started to realize, no, it's too much fuel to fly a steel aircraft. And apparently they started moving to aluminum in early 1980s. So it was a transition. It helped save the fuel from 7.8 gram per cc steel to about 2.7 gram per cc for aluminum. And then the severeness of the climate change was starting around 1990s when people start making very cautious record of how the global temperature is going up, how the pollution is increasing, how the water bodies, land bodies, air bodies are getting polluted over time. And as a result of that, in early 2000, then people realized that no, enough of that. We have to find alternative and better solution. The purpose of life is to move to a better life, not to stick with the older solution, which may be relevant at that point of time because we did not have enough technology, but we have to move on. We have to get smart. And apparently then it was realized in late 90s and early 2000 that magnesium is a viable element. People did research and they found out, hey, wait a minute, magnesium was immensely used in the Second World War time when there was a scarcity of fuel. And now we are facing the same situation. And apparently you see the application of magnesium in defense sector, aerospace sector, transportation sector, marine sector. Everything happened in 1950s at that time. And then after that, when the fuel supply resumed after that, people forgot everything about it and they moved on with the cheaper version. But now the cheapness is not a factor. The climate is a factor now. It's a dominating factor. And as a result of that, magnesium provided a solution. And as Professor Sushanta has already indicated that you get 33 to 35% weight saving when you replace an aluminum component with a magnesium component. So you can see the gravity of how this weight saving can reduce the fuel consumption, and the fuel consumption can reduce the CO2 emission. The CO2 emission can reduce the global warming, and means like in one of the slide I noticed that the glaciers in Kashmir are melting, not in the slide but in the news which I was watching the TV at the same time. The glacier in Kashmir are melting at a much faster pace. So we have to address a solution, and that is why people woke up of magnesium in late 90s and early 2000, and that is where the conscious efforts are being made now to use some magnesium. Steel still provides you a cheaper option. When we do the work in the lab, we provide solution, but at the end of the day, the industrial adoption of that solution takes quite some time because they have to change the whole manufacturing setup and everything, which is not easy to do. Means if I ask you a question that FPS system or foot pound second system is still prevalent in USA when they say of SI units. Why? Because the industry mindset cannot be changed. So now is the time for industry mindset to be changed, and that is where the magnesium has to come in. If we don't come in, someone else will come in. Our next door neighbor China had a vision, and they now control 80% of the market of magnesium. And South Korea has already got its roadmap. So I will say that we woke up a bit later, but at the end of the day, it's still not too late because magnesium is still making inroads, and it is definitely a much better option than aluminum, which if you have noticed in the slide of Professor Shushan, that aluminum is a neurotoxic element. All the Alzheimer's disease and everything, and it's linked with aluminum is already being established way back in 1990s. So apparently it is your choice that you want to use a toxic element and that enters your food chain, or you want to use a non-toxic element that improves your health even if it enters your food chain. So it is a choice to be made, and it has to be choice to be made very quickly to start using magnesium in as many applications as possible. People are already doing it. So it's high time that we also do it in India. So that's my response to your question.
So, Professor Sushanta, have you some additional comments to make on this?
Yeah, so Professor Manoj gave a very nice answer.
Okay, so most of the people say it's really very interesting because you showed some excellent technical applications of magnesium. So there is one question they are asking is, how do you counter the corrosion of magnesium alloys?
What is the question? Can you please repeat?
The question is, how do you stop the corrosion of magnesium alloys? Because magnesium alloys are very prone to corrosion.
Okay. So by doing microstructural engineering, we try to using different alloy design, or by using microstructural engineering, we try to reduce the corrosion impact of magnesium. So yeah.
Yeah, and I can add on to that we have also found that if you put nano reinforcement in there, you can also increase both the dry corrosion and the wet corrosion of magnesium based materials. And another aspect which I plan to propose to Sushant is that you also put in your roadmap the development of coating technology. And I would like to remind that all metals corrode in the wet environment. So there's nothing like which does not corrode. If you look at steel, do you see steel in the engineering application which is not coated, which is not galvanized, which is not painted? But once we get the technique, we are using the steel for 20 years and 30 years with the proper coatings in place. And typically these barriers are twofold, is a galvanized, and then on the top of that, there's a coating. So the development of coating technology has immense importance when we put magnesium into the practice. Micro arc oxidation and other kind of coatings are in place. And with these coatings in the place, we can have the similar corrosion resistance as you see that for aluminum based material and the steel. So technology is there. The question is that the technology is in a few hands. It's with a few countries, and that is where we have to come up, find our own innovative solutions to propose alternative and create our own know-how. But it is being possible. Maruti Suzuki that you drive, its steering wheel is made of magnesium for a very long time, and all these formula cars, many of them have magnesium wheels. So there are magnesium material which can be used as such. So composition control is one of the way in which people are putting rare earth, as Professor Shant has told, microstructural engineering. Compositional engineering is also another way of controlling the rate of corrosion. We have much better understanding now, and it is possible. There's a lot of information in the literature which can be tapped and used to make the corrosion resistant material.
And I will add on to that. So we also have a project in this domain where we want to develop the magnesium aluminum cladding on the magnesium on top and bottom. In many applications, like in ships, marine applications, which is in corrosive environment, they use a alclad material. It means core will be of high strength aluminum, and the surface layer will be of aluminum, another corrosion resistant aluminum. So
Yes.
our one of the objective is like to replace that core aluminum with magnesium. So magnesium will be in the core, and top and bottom the clad material will be of aluminum. So the same aluminum will be subjected to ship environment, and the magnesium will be in the core. So it will not come in contact with the corrosive environment. In that way, we can reduce the weight reduction. Still again for 35 to 40% lighter. We can make that lighter. So we are trying to establish that technology, like how to make this kind of magnesium flat sheets where magnesium will be in the core and top and bottom will be some other corrosive high corrosion materials. And we have also
I think, Sushant, it is quite similar to the alclad technology which was used for the high strength aluminum alloys, and you have to do the simultaneous rolling of these material, and that is quite challenging, but it is a very viable solution.
Yes. And we in our team also we have corrosion experts like Dr. Lakshman. So he is also taking care of the corrosion aspect of magnesium. So we can also improve the corrosion by variety of like microstructural engineering, by allowing some alloying addition, micro alloying, by grain bound engineering. By doing that also we can improve partially the corrosion potential of magnesium.
To add on, Lakshman here, I'm talking on because to add on what Professor Shanta and what Professor Manoj said. From the corrosion perspective, even today we do not know completely about steel. We should admit that. So magnesium also we will capture it. Yes, it is a two-sided problem with magnesium, but we have technologies in hand, as correctly pointed out by the professor, that we can put it to magnesium and make it better corrosion resistant. Especially refining the grains can improve your corrosion passivity point of view as well. So there are strategies which can be applied to magnesium as well.
Okay, so I can see some more questions coming up. So one is asking, what's the application of magnesium in battery, in energy storage, in battery applications, battery and electronic applications?
Yeah. So one of the research group, so magnesium can become can become fuel. And it will produce a lot of energy. So if we make magnesium into magnesium oxide by dipping that magnesium into a solution, then it will consume, it will become fuel very easily. So that group, what they are doing is by using a technology, they burn magnesium easily, and by burning it consumes energy, and that energy is being used as a fuel. Fuel efficiency, fuel transportation. So one team is doing that. They have established that technology and they use so what they do, they take magnesium packs, and in that magnesium pack in a compact unit, and in that they try to burn the magnesium easily, and then it will produce energy, and that energy is used for driving the car. So like that they have done, and they are trying to establish that for the automobiles also, but it is in R&D stage.
Okay, I see some very, very interesting remark for somebody in India. So what he's saying is that I'm from India, one and only one titanium sponge production plant. Our raw material is magnesium. Of course, for the extraction through corrode process, we get the byproduct magnesium chloride. So he's asking, can we recover magnesium from it to get the magnesium instead of importing it from China?
Yeah, Professor Manoj.
Well, I think it can be done. You need the experts in the extractive metallurgy to do that, because if you look at the availability of magnesium in seawater, where the chlorine is there, so I assume that it will be present there in the chloride and hydroxide forms actually. So using the method of electrolysis, it can be done actually. I have not read much about it because I'm not in extractive metallurgy, but it can be done. It can be done.
Okay, I personally think this is a very nice question, because he's very much interested in Make in India, of course.
Yeah.
And there's another question coming up. Professor Sushanta, you mentioned that by using magnesium in car industry, you can reduce the fuel consumption and CO2 emission. So he is asking, how about the energy required first to extract magnesium from its ore? How is the balance between the amount of energy you will be saving through the application of magnesium in mobility sector, and how about the amount of energy you require to extract magnesium from its ore?
So, so there are already standard processes to extract the magnesium. So now the China is the leader in the extractive metallurgy. They are the leader of magnesium manufacturer at present. So there are many players. We have to establish the plants to extract the magnesium. The standard manufacturing processes are already available to extract magnesium from ore. So the different standard processes are there. But in India, we are not extracting because that is not, we have not done till now that. But some industry can take the lead and they can extract the magnesium from the ore, magnesium mineral. In one of the slides, I also told that in India, sea water, plenty of magnesium minerals are available. Now India should take lead. Some manufacturers should take lead to extract the magnesium from the ore. To establish a plant and extract magnesium from the magnesium mineral.
Yeah, and I will add on to that, because the question is asking about the energy calculation. Yes, there are different methods and there are different energy required for producing magnesium from its ore, whether it's a seawater or from the earth crust. And apparently it's an energy intensive process. There are new players coming which are coming with the green technology. I heard 2 or 3 coming from Canada, because the green nature of the extraction is becoming important. Now, how much energy is used to extract magnesium? Well, it's a one-time cost. Someone has to really churn out some numbers to do that. But remember one thing, that the life cycle of magnesium, a typical length of the car can be between say 10 to 20 years actually. So you have to spend energy to extract magnesium, but the kind of fuel saving which comes with the use of magnesium over 10 years time will definitely much more exceed than the energy you use to extract magnesium. And then again, you have to also compare it with how much energy you need to extract aluminum, how much energy you need to extract iron. Of course, iron, the blast furnaces and everything, they also need a lot of energy. Aluminum oxide is highly protective. Alumina, they also need a lot of energy. So magnesium, you should not take as like a absolute value. You have to take the relative value and then look at the advantage. Then you have to do the cost benefit analysis. So someone has to churn the numbers. I'm sure such information is available, but definitely keep in mind the 10-year lifetime cycle for a typical car in a typical country. Of course, some people use it for 20 years, some people use it for 5 years. That's a different story, but the life cycle is about 10 years. So do the calculation on that. You will see that magnesium will fare much better than aluminum and steels.
Okay, so Sushanta, because I have some of the people who just gave me here in my institute the papers, and they didn't join it, but they listened to your seminar, and then they asked me that if magnesium is used in car industry, the most important problem is the shock absorbing structures, because the car has to resist shock to be on the road. So are you planning some fundamental research work along with applied research on the shock absorbing structures from magnesium?
Shock formability, you indicate shock formability or shock as you get in the accident?
What's the amount of energy you will get when you have a shock, car getting into a shock? In the case of the car accident, how much energy is absorbed so the driver is safe?
Well, the energy of impact depends on the mass of the vehicles and the velocity it is hitting at. And currently we have the reasonable strength and reasonable ductility of magnesium, but the mass is lower. And if you have the tension compression asymmetry of about 1, I think the difference can be not too much, if I'm not wrong. And apparently if you design your back and front of the car using the shock absorbing material like the syntactic foams and everything,
Yeah.
then you can mitigate those things. So I think it has to come with the slight modified design features in the modern cars. But apparently I don't see any problem where the vehicle speeds are not very high. But when you go to the highway in the Western countries, the speed can be very high, and low mass and with a similar strength, yes, it may be at slight disadvantage when compared to aluminum.
Yes.
Okay, I think you answered this question.
However, magnesium is also having good damping characteristics.
Yeah, damping is excellent.
Damping characteristics of magnesium is very, very good.
So the comfort of traveling will be much better. You will not see a lot of vibrations coming up and all this thing. And the lot of fretting damage which comes from the vibration will also be minimized. So your durability of the system will be much higher in that situation.
So there's another question is, what time frame should we expect to use magnesium on a larger scale in commercial as well as non-commercial vehicle regarding road transport?
In India or worldwide?
Anywhere.
It is already in pipeline. South Korea has many parts of magnesium in their cars. As I just indicated, Maruti Suzuki is using wheel, and they may be using it more. Many times what the industrial player use the magnesium thing in their bodies, they will not reveal it because it's a trade secret. But in General Motors, is in the boot area. In the Porsche, it's the roof area. In the BMW, it's in the engine area. And there may be the new models coming which are integrating the use of all these different areas and putting in their new models of the car. So it's a very dynamic process. So it is there. People are already putting not only in that, but the truck trailers, the big truck trailers which moves on the highways. The body is made of aluminum, but now it is slowly and gradually being replaced with magnesium, and it saves the weight. So it is in the pipeline. A few things we know, but many things we also don't know at this point of time. But it's already there.
And in 1960 itself, in USA, they have developed a lightweight vehicle that is fully made up of magnesium in 1960. In 1960 region itself, they have developed, the Mercedes-Benz has they developed a full-fledged car in magnesium. So it is already there in international domain. So in India also it will come up.
And in addition to that, Lockheed F-80C, please go and visit the website, completely made of magnesium. Please visit the website, Lockheed F-80C.
So there's one question coming up. There is how do you use magnesium along with plastics? So I think the question is, how do you join aluminum to the plastics?
Well, I think it has to be the same way as you join any other metal with the plastic.
Yes.
Means I don't see any difference between a metal and a plastic, because there are two different categories of material, and they have their own different properties. I don't see any reason why it has to be any different.
So joining, so joining of magnesium with any plastic is like same like any other magnesium is metallic material and plastic is a non-metallic material. It will be same like any joining of any two metallic and non-metallic combination.
Okay. Is somebody asking manufacturing of magnesium composite, is that best through what method? What method is the best for manufacturing of magnesium composites?
Yeah, Professor Manoj is the best person to answer.
Okay, composites. It depends on the end application. Suppose you are looking at small parts, symmetrical parts and all this thing, you can do it by polymetallurgy. But if you're looking at the big parts, then the liquid metallurgy is a better way. So it all depends on the end application. For example, you want to use magnesium in the sheet form. You can't use the polymetallurgy way. You have to go to the casting way and then you have to roll it off. But if you're looking at very, very small, like lamp casing and all this thing, symmetrical parts, polymetallurgy is easily achievable.
Yeah. Yeah. So Professor Manoj Gupta told about the ex situ composite. There is one more version of composite, that is in situ composite. For in situ composite, generally the in situ reaction happens at very high temperature. Around, for example, if you do develop some in situ reinforcement like TiB2 or TiC, the in situ reaction happens at around 900 to 950 degrees centigrade. In that case, the liquid state processing is the only route to develop that kind of in situ composite. But if it is ex situ composite, as Professor Manoj said, both are equally important as per the application requirement. We can go for powder metallurgy route or we can go for liquid state processing route.
Yeah. Actually, you can go for in situ composites also by solid state process, in which you have to take the oxide of a metal which is less stable, and magnesium is much more stable. So if the thermodynamics agrees to that, in some situation it do agree. And like zinc oxide, if you put in magnesium and you heat at moderate temperature, because the melting temperature of zinc is only about 420 degrees centigrade, then in that situation you reduce zinc oxide to zinc and magnesium comes as a reinforcement as magnesium oxide. So there are some headways in the solid state method, but the traditional way of doing in situ is, as Professor Sushant has told, is by the salt, mixed salt process and all this thing, which is a liquid phase method. Yeah, but both the methods are possible.
So somebody asking, can we buy magnesium very easily and to start any new application in India?
That's $1 million question.
Yeah, the question is where to buy magnesium in India?
That's where I was trying to approach practically a lot of government officials and other things, that why we are not extracting magnesium in India, because at this point of time, 80 to 90% of the market is controlled by China. You have other sources of magnesium as well. people are making conscious effort, but they are still not in the market. So you still depend on 2 or 3 players actually, but the cheapest metal you can get from China. And that is where India is way lacking, and we have to put conscious efforts to extract magnesium. South Korea has done that. They started the magnesium program in 2004, and they become uh, means like they really become independent of outside sources. So if they can do it in 10 years time, from 2014 to about 2015, 2004 to 2015, I think India can also do that. So I think that's a very critical direction in which the government has to spend money. We have to have our own source of magnesium.
So just to make things clear, the questions are not from me. The questions are coming from the audience, from people who attended the seminar. So one person is asking that if you have a car made, let us say, of magnesium, and magnesium being very, very light, so you will reduce the weight of the car. So how about the stability of the car because of its weight?
Designing. The
Yeah,
answer
design.
is
Reduction in
designing.
weight.
Yes.
In design only.
Yeah.
Yes.
Answer is design for the center of gravity.
Yes.
And means that is the only solution. It is doable.
So I think you have answered most of the questions I can understand.
Okay.
Can you talk something more about the strength of magnesium?
Strength of magnesium overlaps almost to a level of 60 to 70% of strength of aluminum alloys. It's a band. You can't specify a number to that, because in aluminum alloys, for example, 2000 series will have a different strength than 6000 series, then 7000 series, and the 5000 series or 1000 series. So you can't say a number and compare. It is a band. And in that band, 50 to 60% of that band is overlapped with magnesium. And magnesium also overlap with titanium and steel and nickel also. But it provides you the lightest density. So that is another challenge for us. If we have to increase the application of magnesium, we have to increase the strength band of magnesium. Now, to answer it even more objectively, for the pure magnesium, you can go from 80 megapascal, and very easily you can go up to 300 to 350 megapascal strength level in terms of the yield strength. And in that range, whatever application comes in, you can easily fill that up. The ductility also ranges from 6 to 8%, and it can go as high as 30% depending on the composition and the secondary processing and the primary processing. So you can always have the ductility and strength combination. In the open literature, you see bubble diagrams in which you have this combination, and you can choose the way to make it, choose the combination you want. It all depends on what kind of application you are going for. Load bearing application or non-load bearing application, dry atmosphere or the wet atmosphere. So I hope I answered the question.
Okay, so I think somebody looked at London Stock Exchange, and he's saying that the cost of nickel is around, to 1,300 to 1,400 per kilogram. I don't know whether he's talking about rupees or what currency he's talking about.
Yeah.
But he's saying that the cost of magnesium is around 150 to 200 per kilogram. But why most widely nickel is used and not magnesium?
Well, you have to understand that nickel is targeted. Nickel is heavy, 4 times heavier than magnesium, and we don't talk, when we use magnesium, we talk of the light weighting. So please, you have to understand that these are the 2 different metals with 2 different properties. Nickel is used for making tools. It is used for the high temperature application, nickel based superalloys. So there are 2 different things, like banana is different and mango is different.
I think I have gone through most of the questions.
Yeah. Would you like to pass a closing comment, Professor Sushanta? We can wind up if we're done with all of the questions. So maybe you can take one more.
I think most of the questions are some of the questions are very similar.
Right. Yeah.
Most of the time,
we've answered.
They are overlapping, and the answers have been provided. I think maybe the people who are much more interested, then they may go to the website and have more information on that. And I think you should provide the link for that.
So
and that will be the best thing to do.
So we have our website. You can notice our website in the yellow color mark, like www.appliedmagnesiumresearch.org. So we in this website we have uploaded our like research output also, like our publications, our research based slides. So you can see that, and we will also upload the upcoming events in this website. All of you can go through the website to know about the upcoming events. So we are going to we have planned to schedule an international webinar series and one Mag Talk series every month. The experts of magnesium research will appear and they present their view in this series. So Professor Manoj Gupta is also going to present on, I think, in November. So we are going to schedule his program. So our next meeting is on 21st October, where we are going to inaugurate our group, and we are going to inaugurate the first international webinar series, where one panelist team will be there, and Professor Matthew Barnett will also be there, who will also present about magnesium research. So you please join, see the website regularly to know the upcoming events and upcoming activities of magnesium-based research. So thank you for your participation. You asked so many questions, and we try to answer all of your questions, I think in reasonable good way. So thanks to all. Thanks to the team, Professor Manoj, Professor Gio, Professor Maria, and all the collaborators to be here to moderate this session and to answer the queries from the audience. Thank you, Professor Maria, for becoming the mediator, the moderator of this program. Thank you very much. So, if you have any,
I just want to make last comment. You know, I'm not supposed to be the last one. You have a very good vision of magnesium industry and magnesium applications. And when I see the whole project is very nicely prepared, well drafted, and I hope it will be well managed so that magnesium industry comes back to India, and then it's fruitful for everybody. Thank you very much for associating me with this work. Thank you.
Thank you. Thanks a lot, Professor Mario. It was and Professor Manoj. It was entirely our pleasure to host you. You've spent so much time engaging with us, answering all the questions from the audience. Big thank you to everyone on the panel. Thank you for being with us today, and to all of the participants. I've linked the website on the chats. Please go through the website. Thanks, everyone. Have a good day. Thank you. Thanks a lot.
See you, people. Have a good day.
Thank you, Professor Shanta. Thank you. Bye.
Bye.